All right, this is 2014. Last one on the 2014 exam. This is number 7. This is a little rate question. It's all organic, just like number 6, except it's not all organic. There's just some organic compound or two they give us up here. They give us a little reaction with these organic compounds. This is the initial year of the new format of the test, and I think the national average is like 0.39 out of 4. Mostly because kids didn't get to this question. They ran out of time, and so they said something like 60% of people that took the test this particular year, 60% didn't answer, didn't put anything down for number 7, and then of the 40% that wrote something, only 20% of those got any points at all. And so this is one that's not terribly difficult, but they ran out of time. So anyway. It says the half-life of the catalyzed isomerization of cis-2-butene gas to produce trans-2-butene gas represented above. Measured under various conditions. They give us a little chart. And so again, we talked about this before. Cis means on the same side here. Trans means across those central atoms. Those carbon, that double bond prevents those carbons from twisting, and so trans just means across, cis means on the same side. They give us a chart, various pressures. Pressures are comparable to concentrations. They give us a varying volume in there at one point, and then some temperatures that are consistent here, and then increase in temperature in the last trial, and then half-lives. Half-lives are going to be the key to this problem. So it says in A, the reaction is first order. Explain how the data in the table are consistent with a first order reaction. A first order reaction, the rate can change, but the time of a first order reaction, half-life time of first order reaction will not change no matter what the concentration is. And so even though the pressure or concentration is changing, the half-life time is not changing. That indicates a first order reaction. So I wrote it this way. For a first order reaction, half-life time is independent of concentration or pressure, as long as what is consistent in those things, the temperature is consistent in those first 3 trials. So if we have consistent temperature, we have consistent half-life, as long as we're dealing with first order reactions. That's answer number 1. Good? Good. Letter B says calculate the rate constant for the reaction at 350 Kelvin. Include appropriate units with your answer. My first thought is, if I got a rate constant, then I start rate equals baby K times the concentration of this thing, and trying to solve for the K. The problem is I don't have any rates in this chart anywhere. There's no rates of a change in concentration over a change in time, and so I can't solve for K this way. And then we go into panic mode, like, what do I do? And so this is where, falling back on the formula sheet, this is an equation I gave you. First order reactions all have the same formula to solve for half-lives or Ks. And it's right off the formula chart where the rate constant is going to be equal to 0.693. We derived that in class over half-life time. And so we know the half-life time for the reaction at 350 Kelvin. At 350 Kelvin, the half-life is always 100. And easy does it. 0.693 divided by that 100 seconds will give us a K value of 0.00693, or 6.93 times 10 to the negative third. Units matter here. It asks you for the unit in the question. It's nice if you set it up. There's no unit on that 0.693. The unit on bottom is seconds, so this is over seconds, which should make sense for a first order reaction, right? How many molarities go on bottom? We hold up the one finger because it's first order and take it away. We have no molarities on bottom, just that second unit. And that's it on part B. It's a free point there on part B. It's just a plug and chug problem. You don't even need a calculator to do that. And then C says the initial rate of the reaction in trial 1 is greater than, less than, or equal to the initial rate in trial 2. Justify your answer. And so this is where the rate law comes into play. Now that we have a constant and we kind of know some concentrations or pressures here, we can solve for rates. So the rate expression or rate law is a huge part of your justification. Here, we're looking at trials 1 and 2. What's the difference between trial 1 and 2? The concentration doubles, or the pressure doubles. And so if concentration or pressure doubles, then I would write this out and go cis-2-butene doubling causes the rate to increase in trial 2. That's it. This is a huge piece of the justification. Write the formula out, or the rate expression out, and then it should make sense. If we double this, we should cause the rate to double. Our K is not going to change any because the temperature is the same for trials 1 and 2. K is independent of concentration. It's only dependent on temperature. All K's, equilibrium K's also. And then part D, half-life of the reaction in trial 4 is less than the half-life in trial 1. Explain why in terms of activation energy. So here we go, trial 1 to trial 4. Trial 1 has a temperature of 350, trial 4 has a temperature of 365, and the half-life becomes much smaller, which means this reaction becomes much quicker over time. And so, we talked about this, a 10-degree change in temperature can double a reaction rate in a lot of cases. And so increasing the temperature just a little bit makes a significant decrease in the half-life time. So this is collision theory. If we increase temperature, what's happening? Particles move faster, greater kinetic energy. If particles are moving faster, greater kinetic energy, that means they're going to run into each other more often. If they're running into each other more often, then there are going to be more collisions that have the necessary activation energy to reach that activated complex and cause the reaction to take place. And so make sure when you explain it, you talk about activation energy. I wrote it this way. Higher temperature means higher kinetic energy of particles, greater movement of particles. So the greater number of collisions exist with the necessary energy, or energy necessary to reach the activated complex. Yes, increasing the kinetic energy, there's your activation energy to reach the activated complex. Yes, and that should be our answer there. They're all 1 point. There's 4 pieces of it, so 1 point a pop. That's the end of 2014. That should be the end of daily FRQs for Wednesday for you. Talk to you soon. Bye.